Okay, let us start. So today we are going to deal with the Lyapunov stability of nonlinear systems. So far we have seen Lyapunov stability definitions, and then we have seen Lyapunov stability of linear systems. And today we are going to start with the Lyapunov stability of nonlinear systems. Let us remember. So we call an equilibrium point stable if and only if for any epsilon larger than 0, there exists delta larger than 0, such that the following implication is correct. If the initial condition is inside the delta wall, then the whole trajectory x of t is inside the epsilon wall for all t. That is the definition of Lyapunov stability. Okay? It's our ability to constrain the trajectories of the system around an equilibrium point by constraining the initial conditions. So that is what Lyapunov stability is. So we have defined the local asymptotic stability first. Local, let us say locally asymptotically stable. So the definition of this was containing two factors. The first thing that is required is that it has to be stable in the sense of Lyapunov. Okay? Equilibrium point should be stable in the sense of Lyapunov. And the second condition is that there exists delta such that we have the following implication. If x0 is inside the delta wall, then x of t would go to 0. Okay? That is, we are thinking about the equilibrium point at the origin in this case. And we are saying that for stability, it is sufficient that the trajectories are not diverging around the equilibrium point. But for asymptotic stability, we are requiring also convergence. There should be convergence at least in a delta ball for the initial states. And then we have seen global asymptotically stable in the sense of Lyapunov definition. Globally asymptotically stable in the sense of Lyapunov. And this was defined as follows. It should be, the equilibrium point should be stable in the sense of Lyapunov. And we need to have x of t going to 0 for all initial states. In this case, the convergence to the equilibrium point happens not only in a ball around the origin, but it should happen everywhere. Okay? So we should be free to select any initial state, and the convergence should actually happen for any initial state. So these stability types are, when I go downwards in this list, the stability types would become stronger and stronger. Okay? So here, if an equilibrium point is global asymptotically stable, then it has to be also local asymptotically stable, and it has to be also stable as well. So then we have actually seen the Lyapunov stability of linear systems. Okay? When we look at linear systems, in that case we have the autonomous system x dot is equal to ax. And then the eigenvalues of the matrix A would be important. We are considering the equilibrium point at the origin, and the eigenvalues of A would determine the stability. Let us say that we have n eigenvalues in this case, and I will show them as lambda I. Okay? And we have actually given a theorem for the equilibrium point at the origin. We said that the equilibrium point is globally asymptotically stable. Globally asymptotically stable. This is for only the linear system. It is globally asymptotically stable if and only if lambda i's are actually the real parts of lambda I are all smaller than 0 for all I. Okay? This is an if and only if statement. And it is equivalent to the global asymptotic stability of the equilibrium point at the origin for a linear system. And then we have seen the following. It is stable. The equilibrium point is stable if we have the following condition: real part of lambda i's are actually smaller than or equal to 0, okay? And here we have another condition, multiplicity of lambda I with real part of lambda I equals to 0 is 1, okay? So here this is only an if statement. So if this is satisfied, then we know that the equilibrium point is stable in the sense of the upper norm, okay? But the reverse implication in this case is not correct. This is only an if statement, meaning that if this is satisfied, then we have stability. But if it is stable, then there might still be repeated eigenvalues on the imaginary axis, and that there might be still the equilibrium point might be actually stable. A common example for this is this one. X dot is equal to 0, 0, 0, 0, x. Okay? In this case, we have the system x dot is equal to 0. The whole state space is now filled with equilibrium points, and if we concentrate on the single equilibrium point at the origin, in that case, we will see that it is actually stable. But we see that in this case, the characteristic polynomial d of s is equal to s squared for this matrix, and there are repeated eigenvalues on the imaginary axis. Okay. In this case, this is not satisfied, but this is satisfied. Okay. So that actually means that the reverse implication is not actually correct in general. Okay. So we have seen also the following statement. So we have seen that it is unstable in the sense of the Apuno if there exists I such that real part of lambda I is larger than 0. This was only an if statement as well. Okay? So if there exist eigenvalues in the right half plane, open right half plane, then we have instability. Okay? And the reverse implication is in general not correct. This is only an if statement. Because when the system is unstable, sometimes this condition does not have to be satisfied. And a common example for that is the following: 0, 0, 0, 0, 1, x. The equilibrium point at the origin, so for some initial conditions, this system would give us some ramp-like functions. So it would get unbounded outputs for some initial conditions. And that actually means that for this system, xe is unstable. Xe is equal to 0 is unstable in the sense of the Apuno. Okay? So in this case, we have instability, but this really doesn't imply that there exist eigenvalues in the right half plane. Because in this case, we have both lambda 1 and lambda 2 is equal to 0. There are no eigenvalues in the right half plane. So this system is a counterexample for the fact that the reverse implication is not really correct. Okay? That is what we have seen so far for linear systems in terms of the stability in the sense of the Apuno. So today we are going to start with the stability of nonlinear systems and nonlinear system equilibrium points and how to check them. So when we look at the Apuno stability, of nonlinear systems, in that case we can briefly have two categories, and there are two methods in order to be able to check the nonlinear stability of equilibrium points of nonlinear systems. The first method is called the Apuno's indirect method. Sometimes another name is given to this, and it is called the Lyapunov's first method. These would show exactly the same thing. And this is nothing. Lyapunov's indirect method is nothing but it is stability check by using linearization around an equilibrium point. Okay. So here we decide on the stability of an equilibrium point of a nonlinear system based on the linearization of the nonlinear system around the same equilibrium point. Okay, so we actually linearize the nonlinear the system around the equilibrium point, and we look at the Lyapunov stability of the linearized system. And based on the stability result of that linearized system, we decide on the stability of the equilibrium point of the actual nonlinear system. And that is called Lyapunov's indirect method, or Lyapunov's first method. It is indirect because we connect the stability result of a nonlinear system to the stability of a linearized system. So we decide on stability indirectly based on the linearized system. Okay, that is why it's called Lyapunov's indirect method. And the second type of methods that is used to check the stability is called Lyapunov's direct method. Another name given to this is Lyapunov's second method. And in this case, we don't obtain any linearized system or anything like that. Instead, we actually define some clever energy-like functions. Okay, so these functions are shown like b of x, and these would represent some definition of energy in the system. And based on those functions, whether these functions are decreasing or increasing over the trajectories of the nonlinear system, we actually decide on the stability of an equilibrium point of the system. These functions are called Lyapunov functions, and we will today in the second lecture, when we have time, we will learn that these functions are always going to be something called positive definite functions, because they're going to represent energy stored in the system. And based on these functions, how this function changes on the trajectories of the system, we will be able to decide on the stability of the equilibrium points of the actual nonlinear system directly in that case. And that is why this method is actually called the Lyapunov's direct method. Okay? So we will cover these two methods. So today, in the first lecture, we will try to cover Lyapunov's indirect method. It's going to be something easy, actually, that you might have you might have seen some parts of it in the earlier lectures of this course. But Lyapunov's direct method, maybe you have not seen in the past. And in the second hour, we will start with Lyapunov's direct method. But the first thing that we are going to do is that we will learn what it means for a function to be a positive definite function. And we will learn, for example, what it means for a function to be a negative definite or semi-definite or positive semi-definite function. We will define those function types, and those function types will be critical in understanding the stability decisions using Lyapunov's direct method. But the topic of the first lecture is Lyapunov's indirect method. So in the Lyapunov's indirect method, what we are going to do is that we are going to base our decisions for the equilibrium point of the nonlinear system on the equilibrium points of the linearized system. So here we are going to start with a system x dot is equal to f of x, where we have an equilibrium point xe, where f of xe is equal to 0. This is going to be our system 1. And remember how we do linearization. We define a new variable, x minus xc, which is called z, and then we write the linearized system here, okay? So we write z dot is equal to f times z, where f is the Jacobian matrix of the function f of x here, evaluated at xc. So this is our system 2. In Lyapunov's indirect method, we will base the results on the stability of XC for the actual nonlinear system on the results of the stability of the same equilibrium point for the linearized system. That is what is called Lyapunov's indirect method. It's a simple idea, but it has a fancy name, Lyapunov's indirect method. So here, I will work on some examples first to show you the main idea. So we have first of all, we consider some first order systems. Okay? The system that I will think about first is going to be x dot is equal to sine x, a common system that we have thought about so far. So this x is in R. That is why this system is a first order system. So now if I look at the sine function here on the state space, the sine function is going to be looking like this. I will concentrate on these two equilibrium points. This is xe1, which is equal to 0, and this is xe2, which is equal to pi. Okay? These are the two equilibrium points of this system. X dot is equal to sine x. And here, I could actually put some directions for the motion of the trajectories of this system. So this is nothing but the function sine x, and my state space is the x-axis. So I know that x is increasing here in this interval because sine x is positive, and I know that x is decreasing here, and it is actually decreasing here. I will first concentrate on the first equilibrium point at the origin. So here I will try to compare the behaviors of the actual nonlinear system around this equilibrium point and the behavior of the linearized system around the same equilibrium point. So let us first think about xe1, which is equal to 0. Okay? So in that case, z is going to be x minus xe1. And here my F matrix is going to be del over del x. I have sine x, which is evaluated at x is equal to 0. Okay? So that is going to be my F matrix for this, for the linearization around that equilibrium point. And the derivative of cosine x, and if I evaluate it at x is equal to 0, I see that this F matrix is going to be 1. So here, the linearized system that I obtain in this case is going to be z dot is equal to f times z. F is 1 in this case. So the system that I get is z dot is equal to z. And in this case, since xe1 is equal to 0, this system is nothing but x dot is equal to x. Okay? So in this case, if I try to draw the linearized approximation of the function sine x on top of this figure, I would see that the linearized system is actually going to be using this line as it is dynamics function. Okay? So here, if I show the behavior of the trajectories of the linearized system, then I would put some increasing directions and decreasing directions here for the linearized system. Now let us try to determine the stability behaviors of the equilibrium point for the actual nonlinear system and for the linearized system. Okay? So here, what can you say about the trajectories here? If I take an epsilon ball around the first equilibrium point, will I be able to find a delta ball for the initial states such that if I start the system somewhere inside the delta ball, the trajectories will never go outside the epsilon ball? Do you think I will be able to find such a delta ball for the first equilibrium point? No, that means that this equilibrium point, the actual nonlinear system equilibrium point, is actually unstable in the sense of the Lyapunov. Okay? So I can say that xe1 is unstable in the sense of Lyapunov. This is for the actual nonlinear system. Okay? So what can you say about the stability of the same equilibrium point for the linearized system? For the linearized system, I have exactly the same type of behavior around this equilibrium point. that actually means that XE1 is unstable in the sense of Lyapunov, and this is conclusion for the linearized system. Okay, that is system 2. And in this case, we see an exact match between the result for the actual nonlinear system and the result for the linearized system. Okay, and I will argue that this is happening because this derivative here is actually positive in this case. This F matrix is actually positive in that case. And the positivity gives us a match between the actual nonlinear system behavior and the linearized system behavior when we get very close to the equilibrium point. Okay? So we have instability in both cases. So now let us try to concentrate on the second equilibrium point. XE2 is equal to pi. So I have XE2 is equal to pi in this case. And in this case, if I find F, it is actually going to be the evaluation of the same derivative at pi. And cosine is going to be -1 there. Okay? And that actually means that the system that I obtain in this case is z dot is equal to minus z. Okay? In this case, do you think I can write this system is the same as x dot is equal to minus x? Are these the same system? No, they are not the same system because z here is equal to x minus pi here. Okay? So in this case, if I try to draw the linearized system function here, it's going to be a line here representing the behavior of the linearized system that is looking like this. Okay, and the slope of this line is actually going to be -1. Okay. So now I can look at what the linearized system behavior. Linearized system will have similar type of trajectories to the nonlinear system around that equilibrium point. So what can I say about the stability of the equilibrium point XE2 for the actual nonlinear system? For the actual nonlinear system, if I'm given an epsilon ball, do you think I will be able to find a delta ball around this equilibrium point, which has the property that when I start a system inside this delta ball, the trajectories would always remain inside the epsilon ball? And in this case, the answer is going to be yes. So here, this XE2 is stable in the sense of Lyapunov. So do you think I will be able to find a delta ball in which when I start the system, the trajectories would always converge to this equilibrium point? Can I find such a delta ball around the equilibrium point? Okay? And the answer is going to be yes if I select a small delta here. When I start the system anywhere inside this delta ball, I will see that convergence will happen to the equilibrium point. So now, can I make that delta ball infinitely large? So I can here say that this equilibrium point is locally asymptotically stable. It is at least locally asymptotically stable because I could find a delta ball around in which if I start a system, the trajectories will converge to the equilibrium point. Do you think the equilibrium point is globally asymptotically stable? So for any initial states, do you think we will have convergence to the equilibrium point? The answer is going to be no, actually. If I start the system in the other equilibrium point, the system trajectory will definitely not converge to this equilibrium point. Or if I start the system somewhere here, convergence to that equilibrium point will not happen. Okay? So this system really cannot be, this equilibrium point really cannot be globally asymptotically stable because there are other equilibrium points and there are trajectories which do not converge to this equilibrium point. So here the strongest result that we can say about the equilibrium point for the actual nonlinear system is that XE2 is locally asymptotically stable in the sense of the equal. Okay? That is our conclusion for the actual nonlinear system. And now I will try to look at the linearized system behavior. The linearized system behavior, the trajectories are always the same. If they are to the right of this equilibrium point, if they are started to the right of this equilibrium point, the linearized system trajectories will always come towards the equilibrium point. And if they are started on the left of this equilibrium point, the trajectories would actually always go to the left. I'm looking at this linearized system. Okay, this line actually continues forever. Okay, in that manner. What do you think the stability conclusion for the linearized system for this equilibrium point? Is it going to be stable? This equilibrium point of the linearized system. Consider this line only. Okay, do you think it is stable? It is stable in the sense of the equinox. Is it locally asymptotically stable? Yes. Is it globally asymptotically stable? Yes. So we see that the stability behavior of the asymptotic stability behavior of the actual linearized system is actually a global one. And this is correct in general for linear systems. If you have a form of stability decision, that behavior would be a global property actually. So here we see that XE2 is, in this case, globally asymptotically stable in the sense of the equinox for the linearized system. Okay, this is not for the actual nonlinear system. This is for the linearized system, okay? And this is for the actual nonlinear system. So we see that there is still a match between the behaviors of stability or behavior of convergence. So why is this happening? So why do you think this is happening? In linearization, we are approximating this nonlinear function by a line, and this approximation is only valid in a small operating range. Okay. So it's going to be very, very accurate if we are close to this equilibrium point, but it's not going to be a good approximation when we get far away from the equilibrium point. That means that when we see that a linearized system is actually stable, this really a linearized system equilibrium point is actually stable. This really doesn't mean global stability for the actual nonlinear system equilibrium point. Okay, so based on the linearized system, we can see that the linearized system might be globally asymptotically stable, but that conclusion, we can only carry it to the actual nonlinear system by making it a local property. In general, the nonlinear system equilibrium point can still be globally asymptotically stable sometimes, but we won't understand it by looking at only the linearized system. Okay? So in some way, in these two cases, when these derivatives are actually positive or negative, when this f function, so in this case, this f matrix is a scalar matrix. Okay, it's a 1-by-1 matrix, so its eigenvalues are itself. Okay, so in this case, I have an eigenvalue at 1. It's in the right half plane. Okay. So, and that made us conclude that the linearized system is actually unstable in the sense of the equinox, the equilibrium point of it. So we could actually carry that conclusion to the actual nonlinear system because that derivative is actually non-zero there. And if I get sufficiently close to this equilibrium point, that behavior is going to be replicated, is going to be extremely correct when I get very, very close to the equilibrium point. And on the other hand, in the second case, the derivative was negative, but with that negative derivative, we would still approximate the actual system very well when we get very close to the equilibrium point. And that actually enables us to sometimes to actually conclude that the actual nonlinear system equilibrium point is asymptotically stable when the linearized system equilibrium point is asymptotically stable in the sense of the equinox. but we have to be careful about the local and the global behavior. A linear system will always have a global behavior, and that behavior might not be replicated by the actual nonlinear system, depending on its nonlinearities. So now this is what would happen when the derivatives are actually non-zero. If the derivatives are actually non-zero, the conclusions are similar for the actual nonlinear system and the linearized system. But now let us look at this third example, which is x dot is equal to x cubed. Okay? In this case, again, we have a first order system. And in this case, the x cube is going to behave like this. And we are considering the equilibrium point xe at the origin. Okay? We are looking at its stability. If I linearize this system around this equilibrium point, I will find the function matrix f as del f over del x evaluated at x is equal to xe, which is going to be 0. That actually means that the approximate system that I would obtain when I linearize this system would contain a line with 0 slope. Okay? So in this case, the approximate system that I would like to write would be x dot is equal to 0 times x, which is nothing but x dot is equal to 0. So now I could actually look at the behavior of the nonlinear system trajectories. Nonlinear system trajectories are getting away from the equilibrium point. Okay? What can you say about this equilibrium point? It is in terms of Lyapunov stability. What is your conclusion for the actual nonlinear system for its stability? It is unstable in the sense of Lyapunov. So now I can see that the linearized system also has an equilibrium point at the origin. Okay? What is your conclusion about the stability of that equilibrium point? Is it unstable? So how does the trajectories of the linearized system behave? If I start the trajectory of the linearized system here, how is it going to behave? It's not going to move anywhere. It is x dot is equal to 0. X will not move. Okay? The linearized system is x dot is equal to 0, which actually means that the trajectories of the linearized system will not move anywhere. So here, if for any epsilon ball around this equilibrium point, can you find me a delta ball in which if I start the system, the trajectories will never get outside this epsilon ball? Do you think you will be able to do that? Yes, I can actually take any epsilon which is smaller than, any delta which is smaller than the epsilon value. Okay? And in that case, if I start the system in this delta ball, the trajectories will never, of the linearized system, will never get outside the epsilon ball. That actually means that xe is stable in the sense of Lyapunov. But do you think it is asymptotically stable? No, it is not. For any delta ball around the equilibrium point, I will never find a delta ball which would give me convergence to the actual equilibrium point. So we see that in this case there is actually a mismatch between. So in this case, xc is not asymptotically stable. Yes. Yes, but we are looking at the stability of the equilibrium point at the origin. Okay? The linearized system trajectories are stationary. They're not moving anywhere. So we see that there is actually a mismatch between the actual nonlinear behavior and the linearized system behavior. Why is this happening? Yes. Yes. So here, when we look at this function f of x around an equilibrium point, we have the following Taylor series expansion, del f over del x, evaluated at x is equal to xe, x minus xe. So here, plus del square f over del x squared, 1 over 2, x is equal to xe, x minus xe, plus some higher order terms. Okay? In linearization, we are actually neglecting all of these terms. Okay? So, and this thing is actually 0. And when this derivative is not actually 0, if it is non-zero in magnitude, by making x infinitesimally close to xe, I could the approximation of neglecting these higher terms would start becoming correct. Okay? So here, if this thing is actually non-zero, in that case, if x is very, very close, if x is sufficiently close to xe, I could actually neglect these higher order terms. Because if this is epsilon, then this is going to be epsilon squared, and I will have epsilon cubed coming from the other terms. If this is non-zero, if it is 5, then or if it is minus 5, it really doesn't matter. If I get close to, I will have 5 epsilon plus, maybe this is, I'm making it up, 17 times epsilon squared plus 15 times epsilon cubed, etc. If epsilon is very small, neglecting these terms would give us a very good approximation for small epsilon values. But here, if this derivative is exactly 0, in that case, neglecting these higher order terms really does not make much sense. Okay? And when this derivative is actually 0, this actually means that the stability behavior of the actual nonlinear system is actually going to be determined by these higher order terms, which we neglect in our linearization. Okay? So here, this is why there can be a mismatch in the case that we have a zero derivative here. When this is 0, higher order terms will determine the stability of the equilibrium point of the actual nonlinear system. In the linearized system, since we are neglecting these important terms for the nonlinear system, then we can get a mismatch in the results of stability for the actual nonlinear system and the linearized system. So there might be other type of mismatches. For example, if I consider the system x dot is equal to minus x cubed. Okay? If I consider this system, in that case, minus x cubed is going to be looking like this. What can you say for the stability of the equilibrium point as the origin for this nonlinear system? It is going to be stable in the sense of the envelope. Is it going to be asymptotically stable? Yes. And is it going to be globally asymptotically stable? Yes. So this equilibrium point is actually globally asymptotically stable in the sense of the envelope for the actual nonlinear system. And that is what I'm looking for. But when I look at the linearized approximation of this system around that equilibrium point, it's going to give us exactly the same system, okay? Because we are neglecting the higher order terms, we get the same first order term for both cases. And in this case, although the equilibrium point of this system is actually globally asymptotically stable, we see that in the linearized system there is no asymptotic stability in its equilibrium point. There is again a mismatch between the results. So in the case that we have larger higher order systems, in that case, what is going to be important is going to be whether the real parts of the eigenvalues are zero or not. In the case of a second order system, if we have x dot is equal to f of x, we can linearize it. And in that case, what is going to be important for us is the real parts of the eigenvalues of this F matrix. If the real parts are non-zero, then we will be able to carry the stability result for the equilibrium point of the linearized system to the nonlinear system. But if there are eigenvalues with zero real parts, in that case, sometimes the stability result for the linearized system might not be carried or might not be correct for the actual nonlinear system. In the first order case, the stability results might change between the linearized and the actual systems if this derivative is actually zero. In the higher order cases, real parts becoming zero or not would start becoming important in that case. Okay? So that is actually what the theorem related to the Lyapunov's indirect method will actually say to us. Let us now write the theorem for the Lyapunov's indirect method. So this is the main theorem for Lyapunov's indirect method. So here it is going to contain three parts. So if the linearized system is globally asymptotically stable, in the sense of Lyapunov. This means that all of the eigenvalues, their real parts, are actually smaller than zero for all I. Okay? All eigenvalues are in the open left-half plane. Then, the equilibrium point of the nonlinear system is locally asymptotically stable. In the sense of here. So here there is some important distinction. If all of the eigenvalues of the linearized system, if they are all in the open left-half plane, okay? In that case, those higher order terms will not be important for us. If we get sufficiently close to the equilibrium point, the first order terms will be a very good approximation in the Taylor series expansion. Okay? If all eigenvalues of the linearized system F matrix, if they are in the open left-half plane, in this case, the equilibrium point, xc is equal to 0 of the linearized system is globally asymptotically stable. A linear system will show global asymptotically stable behavior. Okay? But in this case, we will be able to conclude that the actual nonlinear system equilibrium point is asymptotically stable. We will be able to ensure that if there exists a delta ball around the equilibrium point, and if you get sufficiently close, if you make this delta ball sufficiently small, in that case convergence will happen for all initial conditions in that delta ball. So in that case we will actually know that the equilibrium point of the actual nonlinear system is asymptotically stable. But we will not know whether it's local or global asymptotic stability. Okay? So here we are guaranteeing that it is locally asymptotically stable, but we will not know. The theorem will not say anything about global asymptotic stability. It might be global asymptotic stable, or it might not be global asymptotic stable. We cannot decide it by using linearization. Okay, that is the result that the theorem is stating. So let us look at the second part of the theorem. The second part of the theorem is saying the following: if the linearized system, in this case, I'm talking about the F matrix of the linearized system, has at least one eigenvalue in open right half plane. Okay? This means that there exists I such that real part of lambda I is actually larger than 0. Okay? Then the equilibrium point of the nonlinear system is, what am I going to say? Unstable. If there exists an eigenvalue here in the right half plane, it is like the case in the sine function. Okay? In the sine function, the slope was positive. So when I get sufficiently close to the equilibrium point, I see divergence in that case. So when this is positive, the higher order terms, if we get sufficiently close to the equilibrium point, the higher order terms would indeed be unimportant. Okay? In that case, that is going to define the asymptotic behavior in a small neighborhood. Okay? So in that case, the equilibrium point of the nonlinear system is unstable in the sense of the upper. So this was the second part of the theorem. Actually, these are all that we could say. The third part is going to say that the theorem will not say anything in some cases. Okay? The third part is if all eigenvalues of the F matrix the linearized system are in open left half plane, which means real part of lambda I is strictly smaller than 0, except for one or more eigenvalues on the imaginary axis. Meaning real part of lambda I is equal to 0. Then we cannot make a conclusion about the stability or instability of the equilibrium point of the nonlinear system. Based on the linearized system. So in this case, Lyapunov's indirect method is inconclusive. Okay? You cannot say anything about the stability or instability of the equilibrium point based on the linearized system. So if all of the eigenvalues are in the open left half plane, except for some on the imaginary axis, okay? In that case, the same case is actually happening. In some directions, so in some directions of the state space, this derivative is actually disappearing, okay? So if there exists actually an eigenvalue on the imaginary axis, in some directions on the state space, this derivative is actually disappearing. Okay? When this derivative disappears, the higher order terms might dominate. And when those dominate, then we might have an unstable behavior, a stable behavior. It will depend on these higher order terms, what these higher order terms are. In that case, the sole linearization will not give you any information about the stability of the equilibrium point of the nonlinear system. Let us give a break. We can meet back at 4 again. 45 geçe tekrar buluşuruz.